Okay, so for this first lesson, we are looking at section 2.1, which is just about limits. So calculus in general is the study of infinitesimal, it's just really small change. Business calculus, we're going to look at the effects of small changes on an overall outcome. And so to do this, we need to understand, we need to look at functions that are nice enough, and we need to figure out what that means. So we have this function f of x equals x squared plus x minus 6 divided by x minus 2. And the question is this a nice function? The answer is yes, almost everywhere. Let me change this. My daughter's been playing with this. That's very, let's see, so here, maybe here. Okay, so what do we know about the domain of this function? Well, we can't divide by 0, so 2 isn't in the domain. And if we think about this function, there's actually a hole there. Let me show you why. So if you look at that top part, factors to x plus 3, x minus 2, and then the bottom is x minus 2. So those like cancel. So you're looking at basically the graph of x plus 3 with a hole when x is 2. So it's like this, but with a hole right here at x equals 2. Okay, so what's the behavior around 2? Well, the y values, if you just look at that graph, you can't tell if there's a hole there, right? So it looks like the y values are close to 5. When the x values are close to 2, and that's a limit. So the idea here is that you're looking near a point. That's the whole idea of a limit, is what's happening as the x values get really, really, really close, infinitesimally close to the x value. So we can actually do this with a table. So in Desmos, go to desmos.com and you can do this, but you look and I have graphed here f of x equals x squared plus x minus 6 over x minus 2. That's the function we're looking at. So you hit that tool thing and you can use the table and then just type in these values for x. So we're looking at 1 and then 1.5 and then 1.9 and then 1.99 and 1.999. A lot of 9s. Okay. And then we can put those in. So we have 4, 4.5, 4.9, 4.99, and 4.999. So 4, 4.5, 4.9, 4.99, and 4.999. So you can see these values are getting close to 2, and these values are getting close to 5. And this is from the left of 2. And so we can do a similar thing from the right. So I'm going to go back to Desmos and do so really close to 2 would be 2.0, goodness gracious, 2.001, 2.01, goodness, 2.01, 2.1, maybe 2.5, and then 2.3, or just 3, sorry. Okay, so you're looking at 5.001, 5.01, 5.1, 5.5, and then 6. We'll go back to here and put that in. We have 5.001, 5.01, 5.1, 5.5, and 6. So you can see these are getting close to 5 as you move that way, and these are getting close to 2 as you move toward 2. So this is the idea of a left-hand limit and a right-hand limit. One way that I like to do this is think about putting your left hand on the graph and move toward, go on the left side of 2 and move toward 2. And what y value would you be approaching? That's 5. So the left-hand limit is 5. And you can see that that notation is this little negative, like as an exponent, that's coming from the negative side of 2 or the left-hand side of 2. And then similarly, the right-hand limit, get on the right-hand side of 2, move closer to 2, the x value 2, see what y value you're approaching. It is also 5. Or look at your chart, getting close to 2 from the positive side. That's what that little plus is for. So from the positive side of 2, bigger than 2, getting closer to 2, the y values get close to 5. That is your right-hand limit. So something to note here is that not all functions have the same left and right-hand limits. Okay, so again, left-hand limit is going to have a negative as the exponent. A right-hand limit would have the plus sign as the exponent. Okay, so let's look at this piecewise function. We have 1/2 x when x is between 0 and 4. So between 0 and 4, we're looking at 1/2 x. So when x is 1, when x is 2, the y value would be 1. When x is 4, the y value would be 2. And we can use a closed circle there because of that equal to, and then 0 here. Okay, so we have this line. Ugh. Okay. And then for this next one, we have x minus 1 when x is bigger than 4. So a y-intercept of -1. Yeah, and that's open there. We want to start over here. So let's just like plug in, I don't know, plug in 4 and the value would be 3, right? And you plug in 4, plug in 5, the value would be 4. Plug in 6, the value would be 5. And so you have this line up here. And then you have this like open circle here because this is just greater than 4. Okay. So if we are trying to figure out what the left-hand limit is, that's what this is. So the limit as x goes to 4 from the left of g of x. So from the left, which side here is from the left? That would be the pink one. We would want to be on the pink piece of the graph here to approach 4 from the left. And that y value that we are approaching is 2. And then if you're looking at the limit as x goes to 4 from the right-hand side of g of x, you're looking at the green piece of this function. Get close to 4 from the right. What y value are you approaching? That would be 3. So this is the right of 4, and this would be the left of 4. Okay, so right, again, one-sided limits, sometimes they're the same and sometimes they're different. So sometimes we'll write this as just a one-sided limit, and that's when you would have those, the exponents like here and here, which tells you which side you're coming from, or just a regular limit without putting that in there. So if the values of f of x approach the same number, wait, that is a lot of words. Basically, if the left-hand limit equals the right-hand limit, then the value L is the limit. This is wordy. So if the left-hand limit equals L and the right-hand limit equals L, then the limit equals L. That's basically what it's saying. So if we go back to our example up here, the left-hand limit was 5, the right-hand limit was 5. So together, the limit is 5, and you would just write that like this. The limit as x goes to 2 of f of x is 5. Okay. So what does the value of the function at c tell you about the limit as the function approaches c? The value of the function at c So look at this one right up here. What does knowing what the value at x equals 4 tell you about the limit? The answer is nothing. We want to know what's happening near a point, not what's happening at a point. So knowing what's happening at the point tells us nothing about it. If the limit exists at C, then what do you know about the one-sided limit? That they both equal C. So again, like that one we did up at the beginning, the left and right hand limits were both equal to 5. The limit exists and is 5, and so both the left and right hand limits are 5. Okay, so here's basically what all of that is summarized as saying. For a function f and a real number t, if the left hand limit of f of x is L and the right hand limit is L, then the limit altogether is equal to L. So the limit as x approaches t of f of x equals L. So the limit exists if and only if L is a real number. You don't want to approach an imaginary number. And if the left-hand limit and the right-hand limits do not equal, then the limit does not exist. Often that would be abbreviated as a D and E. All right, so here's our first example. That's the function we did at the very beginning. The left and right-hand limits were both 5, so the limit is 5. F at 2, this was a whole, and so the function is undefined there. Then we have g of x is equal to this piecewise function. We did this as well. So the limit as x goes to 4 does not exist. The limit as x goes to 4 of g of x does not exist because the left-hand limit was 2 and the right-hand limit was 3, so they were not equal. This was the left-hand limit and this was the right-hand limit. G of 4 was 2, I believe. Okay. What do we say? What do we mean when we say that f of x is a nice function? That the limit exists everywhere. The limit exists everywhere. So really nice functions would be continuous functions, which would mean that the limit exists everywhere. Continuous functions. Limit exists everywhere. And the function value equals the value of the limit. Okay, so those are super nice functions. Polynomials are super nice functions because they're continuous, so their limits exist everywhere, and the function value equals the value of the limit. So the limit as x goes to a of p of x is just p of a. Now that's a complicated way of saying just plug in the value and you'll have your answer. So looking at this one, as we approach, as you look at this, so polynomials are nice, you just plug in and you're good to go. But looking at this one, if we plug in 7, this is undefined, right? Because we would be dividing by 7. So what we want to do, can't plug in 7, we will get 0 over 0, which is bad. So what we would do instead is kind of build a table or look at the graph. So if we do x and f of x, and you can do this in Desmos or in a calculator, put the function in the calculator under y equals, and then do second trace or second table, and you should be able to look at the table, or second graph, and that'll give you the table. If you do second window, you can change the x value to ask, and then you can type in 6.9, 6.99, 6.999. We're getting close to 7 from the left, so 6.9, 6.99, 6.999. And when we plug that in, we get 13.9, 13.99, 13.999. So this value, the value of this limit, the thing we are approaching, is 14. These are getting close to 7. These are getting close to 14. The 7 from the left, right? Alrighty. Number 2, we have the limit as x goes to 0 from the left of the square root of 4 plus h over h. And what we want to do is look at this. If we plug in 0, right, we would have the square root of 4 over 0, just 2 over 0, which is undefined. So this limit does not exist. All right. And then number 3, we have this another rational function, x squared minus 4 over x plus 2. If you do this, you can sort of, I will actually show you this in a minute. So we'll look at the table right now. By the table, when you plug in these values for x, you get negative 3, negative 3.4, negative 3.9, negative 3.99, negative 3.999. So these values are approaching 4, negative 4, as these values approach negative 2. Why am I approaching negative 2? I have no idea. That's not right. That's not right.